Hello everyone, welcome to the third lecture of second week of our course on AI for Earth observation. In the previous lecture, we started talking about the classification or semantic segmentation approaches, basically the machine learning approaches that we used before the era of deep learning, with a few specific examples. We convinced ourselves that indeed support vector machine SVM was one of the popular approaches during that time. And as we have said that this is not the case, that SVM is not used anymore right now. Even now, if you refer to one of the remote sensing conferences program details, you will see that there are always one or two works which still uses SVM, and indeed there are contexts where maybe using SVM or one of the other approaches that we study today makes more sense rather than just blindly adopting deep learning. In the last lecture, then we have discussed a bit about how SVM, rather linear SVM, works. We have also seen eventually a soft margin version of it. With this background, let us take our discussion forward. What we have seen in the last lecture is a linear version of SVM. However, it's indeed the case that many real-world datasets or real-world applications, you cannot just differentiate between the different classes using a single straight line or hyperplane. And here the point to be emphasized is that what we are talking about is not just a few misclassification or noisy data, which we saw in the last lecture that we can possibly handle with soft margin version of SVM. We, in this case, we are saying that, okay, like this particular data, let's say, this is indeed not just linearly separable. So in such case, one possibility is, instead of separating the data in the original input space, to transform it into a new feature space. In the transform space, the data that was not originally linearly separable, this becomes linearly separable in this transform space, so that we can then apply SVM in this transformed space. So what we are doing is we are training linear SVM in this new feature space, whereas if you view back in the original space, the resulting decision boundary is still nonlinear. So I've not shown any particular example here. However, work out this on your own. Try to find example where data was, let's say, like originally not linearly separable. Think of something like, let's say, like data lying in concentric circles or something like that. And then try to think of some kind of transformation that in the new space, the data becomes linearly separable. So with this, the idea that nonlinear SVM uses, and we'll just touch upon this. We are not going into the details of this. They use the concept of kernels. So explicitly, it transforms data into a higher dimensional space. This can be computationally expensive. Thus, what SVM does is it uses kernel functions to compute similarities. So, with this background, so what we have seen till now, we have seen the linear version. Indeed, we have seen the linear version of the SVM that basically forms the actual mathematical backbone of SVM, right? So this we have seen in a bit more details. We have seen the soft margin version also. Thereby now we just discussed the nonlinear version. However, like not into much detail. So if you're curious, of course, you can study on your own. Another important aspect that needs to be also discussed quickly is multiclass SVM. So already in the last lecture, I had mentioned that SVM, this indeed is for two classes, whereas the multiclass version is possible, right? We already saw a particular paper example where in the context of Earth observation data, they applied or designed multiclass version of SVM. However, we did not, of course, discuss the details of that paper at that point. So now let us try to understand this multiclass SVM in a bit more details. Standard SVM is designed for binary classification. The multiclass SVM, in this case, will be extending the binary SVM by combining several binary classifiers. So how can we combine several binary classifiers? Take a pause at this slide. Think about this on your own before going ahead. Okay, so one straightforward approach is designing one versus rest classifiers. That is, if we are given a problem with n classes, we can train n binary SVM classifiers such that each classifier separates one class. So you pick up one class at a time and you design a classifier such that this classifier separates this one class from all the remaining classes. Then you pick up another class and you design another classifier such that this new class is again separated from all the remaining classes. During prediction, every classifier produces a decision score. The class with the highest decision score you can assign to the test sample. Another straightforward variation is one versus one classifier. That is, train one classifier for every pair of classes. So we had n classes. So the first one, take it and like design classifier for all the n-1 rest classes. Take the next one. So this has already been accounted once. So we are designing it for remaining n-2 classes. So this now is like a sum, right? n-1 plus n-2, like this. This sum is equal to n-1 by 2. Then eventually when you're using this, what happens is that each classifier votes for one of the two classes it was trained on. The class receiving the maximum number of votes can become final prediction. Of course, variations can be done here also. Now, we have already seen a few examples of how SVM was used in several classification, semantic segmentation, hyperspectral classification use cases in pre-deep learning era. The question one could ask is that, is it the case that SVMs were just restricted to such straightforward classifications or pixel-wise classification, which we call semantic segmentation, such use cases? Or they were also used for more complex cases? And indeed, the answer is SVMs were adopted also in more challenging remote sensing problem settings, such as domain adaptation. Domain adaptation we will be discussing in more details later in the context of deep learning. However, let us now try to see one particular example of domain adaptation with SVM, which was devised before the deep learning storm that came from 2011 or so. So this particular example, DSVM, in this, a SVM-based domain adaptation approach is designed for remote sensing data. In this, the assumption is that we are working with two domains, source domain and target domain, and they have different data distributions. Now, the source domain, we have label data. So SVM, we need label data to train SVM, right? So obviously we'll start with training SVM on the labeled source domain samples. On the other hand, for the target domain, we do not have label data. What we do here is iteratively incorporate reliable information from the unlabeled target domain samples. That is, you have the target domain data, unlabeled data, you have the source domain trained SVM. You can use that trained SVM to understand the target domain data and understand, like, okay, which of those target domain data you are more confident on and you can include in your training set. So what happens is that at each iteration, the influence of the source domain samples is gradually reduced, whereas the influence of the target domain samples is increased. Now, this DSVM work, interestingly, also proposes a circular validation strategy. That is, at the very first step, we are doing the forward adaptation. That is, adapt the classifier from the source domain to the target domain. Source domain, we have label data. Target domain, we don't have label data, but we said that, okay, let's train our SVM classifier on the source domain first and then slowly include the target domain samples so that we are reducing the source domain impact on this classifier and increasing the target domain influence. This is the step one, which we discussed in the last slide. However, target domain, we indeed don't have any label data, right? So how do we know that this adaptation is working? And there comes the idea of backward adaptation. What is backward adaptation? What we can do is, once we have predicted the target data, all the target data, let's say, we can treat those as pseudo labels, and we can now adapt back the classifier to the source domain. And we indeed, so when we are adapting back to the source domain, we are now assuming as if we don't have the source domain labels, but we have them, right? Actually, we have the source domain labels. Since the source labels are known, we can actually evaluate the recovered classifier on source data. Good recovery of source domain performance will indicate that the forward adaptation likely learned a meaningful target domain classifier, because if the forward adaptation failed, it's very unlikely that the backward adaptation will lead you to a meaningful classifier now for the source domain, right? Because this is a two-step process. If one of the steps fails, of course, the entire pipeline fails. So this is the assumption behind circular validation. Indeed, this particular concept in slightly different manner is also used later in the deep learning era, not just in the context of, let's say, domain adaptation, also in the context of when we will study generative approaches such as GAN, generative adversarial network, we'll see particular modification or versions of them which kind of uses this kind of circular strategy. So before moving ahead from support vector machine, let us try to summarize the reasons of popularity of support vector machine. Support vector machine requires relatively few labeled samples. This is robust in high dimensional spaces, the reason we see SVM used quite a lot for the hyperspectral images. And it also comes with a strong mathematical background, thus instilling more confidence, like in the researchers who want to use SVM. Important point to note is that even though we introduced SVM in the context of classification, it can also be used for regression as well. Now, let us take a moment to think about, like, if we had to use SVM as a, let's say, as a user. I'm not saying that, okay, actually implement the entire SVM algorithm from scratch, rather just as a user with Python, what are the options we have? This indeed is like well available with all programming languages of the programming platforms. So right now, most of us uses Python. This is available in Python with scikit-learn. So let us see a very simple example. Here, what we see in the first line, we have imported the SVM, and now we have taken this particular data points, 5 of them, which in the next line we are giving the particular labels. We are giving labels like 2 different classes, let's say 00011. And if you look at the data X, just try to visualize this, or even take a paper and try to plot those points. It will become very it's not that difficult to understand that what we are doing with this data. So it's a very simple example. And now when we are trying to predict this new data point, text data point 010, it's quite easy to guess what would be the label, right? Similarly, when we are trying to predict 3.1, what would be the label? So that's given right now here. The output in the first example is 0, whereas output in the second example is 1. Okay, with this, now let us move ahead from support vector machine. The next approach that we'll briefly talk is decision tree. We will spend just a few minutes on decision tree, and then actually on the top of the decision tree, we will move ahead to another approach which builds on the top of the decision tree. So decision tree is again a supervised learning algorithm. It makes predictions by recursively splitting data based on feature values. Each internal node in this tree represents a decision rule, whereas each branch represents an outcome and each leaf node represents a prediction. Decision tree is indeed quite intuitive model, and thus it is easy to interpret. So we'll see a visual example, a very simple example. You see, like there are two classes. Think of these two axes, x1 and x2, and what we see is that, let's say if we split the data along the x1, okay, and we say like, okay, x1 greater than 0.5 or x1 not greater than 0.5. So accordingly, again, now what we can do is we can split now based on the x2, and there are two different possibilities available. One possibility is that x2 that is greater than 0.6, another possibility is that x2 this is greater than 0.5. So in these two cases, the output prediction is our like the red class, right? We see this red and the black color, so let's call our classes by those names. Whereas the other two cases, if x2 is less than 0.6 or less than 0.5, in the two different branches of this tree, we are seeing the black class. So often in the decision tree, entropy or the information gain concept is used for choosing split. How it works? Entropy measures the impurity or uncertainty of a dataset. Information gain measures the reduction in entropy after splitting on a particular feature. At each node, the decision tree thus evaluates the possible candidate splits and selects the one with the highest information gain, since it results in the greatest reduction in uncertainty about the class labels. Now with this, let us try to also formalize a bit some definitions on the errors. Training errors, very straightforward. We have a training set, the error committed on this, we'll call this as training error. Test error, again, we have a test set, the error committed on this set, we will call this as test error. Similarly, we can also, or we often hear also this name generalization error. So this is expected error of a model over random selection of data from same distribution. Let us also try to understand a bit about underfitting and overfitting. Underfitting happens often when the model is too simple, and in this case, both training and test errors are often large. Whereas in the case of overfitting, generally the training error is small, but test error is large. And overfitting happens quite often when the model is complex. So with this, we can try to understand a bit more about the potential reasons for model overfitting. Limited training data size often leads to model overfitting. Indeed, training dataset size is a very important aspect in our machine learning or deep learning. One of the important catalysts that allowed the development of the deep networks is indeed development of datasets like ImageNet, and eventually also when we see like the transition from CNN based approaches to transformer based approaches, also we see a similar kind of like explosion in the dataset size, or at least explosion in the even if not supervised dataset size. At that point of time there was already like self-supervised techniques, so possibility to use larger dataset even if not supervised manner. So this dataset size, this is of course one of the very important aspects if you're just trying to train a model from scratch. And so training from scratch indeed is a bit like also a word, I would say, like more in the deep learning context, we are not yet there, right? So yeah, I mean, at this point of time, just try to understand, okay, like you have the data set, and depending on like data set size is small, I mean, this may lead to model overfitting. Also, the issue could arise from non-representative training examples. So you have like, let's say, large data set, but like your training example, this doesn't represent your entire data universe. This just represents silos. In that case, it would not work, right? So let's say you want to train some kind of like building functionality classification on, let's say, the entire Delhi NCR. However, your training data, let's say for some reason, is only from South Delhi. Do you think that this will generalize to all residential pockets of Delhi NCR? It would not, right? Because there is strong difference within the NCR itself. The other reason is high model complexity. So given two models of similar generalization errors, it makes sense to choose the simpler model over the more complex model. So in the terms of decision tree, try to think on yourself, like which model we call as more complex, which model we call simpler. And with this, before moving ahead, let us try to understand again, like why are we interested in the decision trees? Because they are indeed easy to understand, easy to visualize. They are able to capture nonlinear relationships. However, decision trees are often prone to overfitting, and this forms the background for our subsequent discussion, which we will take forward in the next lecture. Thank you.